Okay. Uh, and most of you, almost everybody ran into some pitfall or another. But you're doing a lot of the right stuff, okay? So let's see how to carry it through. So let's say that my A and B numbers are my G, A and D numbers are 21 and 6, and then 12 and 10. Okay, so that means that my points ought to be, okay, again, the situation, and this is the video. Situation is you have a radioactive sample, has an activity of 21 after 6 days. Of course, the activity goes down. So after 12 days, sorry, after 10 days, 4 days later, the activity is all the way down to 12, right? It's fallen almost to half of what it was. Okay. If I put this information on a graph of y equals the activity versus t measured in days, then what do I need? I need 21 days out. So I'm going to put 20 here. So 10 goes here, 15 goes here, and 5 goes here. And that was really done because that should be my activity. So I'm going to put my activity. I'm going to do what I did on the x-axis, on the y-axis, which is where those numbers should go. And then my days run from 6 to 10. So what I want to do is I want to go ahead and do a scale here that illustrates this. The long-term behavior a little better. So I'm going to go all the way out to 16 here. So this would be 8, this would be 12, and this would be 4. Then I'm going to take the 20 up here. I use 20 because I can divide it into 4 pieces. And clearly 25 will be another piece higher than 20. Okay, so now after 6 days, the activity is 21. So where's 6? Well, 6 is 10. And 21 would be about here. That'll give me a point. 6 days, 21 units of activity. Then after 10 days, and of course 10 is here, we're down to an activity of 12 units. So 12 would be about here. Now, an exponential function has to be asymptotic to the horizontal axis. How are we going to get an asymptote to the horizontal axis using an exponential curve, or the shape of an exponential curve? Well, it's going to have to be something like this. That might or might not be a good model, but that's kind of the way it looks. Might not be as curvy as that, but pretty much has to be about that curvy in order to get the asymptote. Of course, here, you want to be careful. I've drawn this as though there's a vertical asymptote up here, just because of the curvature that I put on it. But it doesn't have a vertical asymptote. Remember, an exponential function has a graph that looks like this. And if you have a value of the base that's negative, it's going to look like this. Okay, those are two basic shapes. And of course, you can raise or lower the graphs, but that's not the case. It's just kind of a model. Your open math defines an exponential function as an AB to the X function. Okay. If you wanted to vertically shift it, it'd be AB to the X plus some constant. It wouldn't be a strict exponential function anymore, but it would still be, I still kind of call it an exponential function. Okay, that's not important. What's important is we've got 2 points in this graph, and we've got the form of the function, and there are 2 things that are unknown in the form of the function, A and B. If I've got a number for A and a number for B, then I've got my function. And I can plug in X and I can get Y. I could plug in Y and solve for X, at least once we know a little bit about how to use logarithms. Okay. So we have Y equals AB to the X. Well, Y equals 21 when X equals 6. And you know what? I'm using T here. And what I really should have said, it doesn't matter if you use X or T, but just to put this in context, I'm going to start using T instead of X for my time, because that's how I labeled my graph. Should have done that in the first place. You probably used X, that's fine. But if you looked at the graph, maybe use T, that's also fine. The arithmetic and the algebra is all going to be the same. Okay, so we know Y equals 21 when T is 6, and Y equals 12 when T equals 10. Oh, Y equals AB to the T. Y is 21 when T is 6. So we get 21 equals AB to the 6th. Of course, that corresponds to the coordinates of this point, which are 6, 21. And this one is 10, 12. Well, Y equals 12 when X equals 10, so that 12 equals AB to the 10th. Fair enough? Well, we've got 2 equations. We've got 2 simultaneous equations that we need to solve for A and B. Two unknowns, 2 equations. We got 2 equations and 2 unknowns. Then, if algebra is up to the task, we can solve it. Sometimes algebra just isn't up to the task of solving an equation. Okay, nobody's algebra is up to it. And then you got to do weird things. You don't worry about that. Your algebra will be up to it. And the algebra is not particularly difficult. You just have to understand the laws of exponents and apply them correctly. And of course, open math, there's at least one problem in open math. We had to do this. And I can see that in your work. Okay, you've done a pretty good job there. I want to make sure it's really solid. Okay, so call this equation 1. Call this equation 2. What do we do to solve these equations? Somebody who wasn't. Okay, so the way open math has told you to solve this equation, you isolate one of the variables. That's a good way to say it. That's the answer I got, which means you solve one of the equations for one of the variables. Okay. Now, let's just take the first equation. Which variable are you going to want to solve it for? You want to solve for A, or are you going to want to solve it for B? Which one's easier to solve it for? How many think A is easier to solve it for? How many think it would be easier to solve it for B? Nobody seems to think that, and you're right. To solve it for B, you're going to have to take a 1/6 power or 6th root of both sides. You could do it. It would work just fine. It'd just be a little more trouble. Not that much more, it turns out, but okay. We're going to solve equation 1 for A because that's really easy. And I don't even have to write out the steps. We just divide both sides by B to the 6th. If we tried to solve for B, we'd have to divide both sides by A and then take the 1/6 power of both sides. So it's a lot easier to solve this for A. Now, hopefully, we plug this into the second equation. So we're going to replace A by 21 over B to the 6th. And in case you're having trouble seeing where all that comes from, first equation gave us this. And now, just so I can draw arrows going everywhere, I take this and I plug it in here, which gives us this. Okay, A is 21 over 6, so A is going to be, or 21 over B to the 6th. So A is going to be 21 over B to the 6th. And we have this equation. Now, how many unknowns do we have in this equation? 1, which is B. So we can solve it for B. All we have to do is apply the laws of exponents. Well, first thing I'm going to do is I'm going to simplify this side. B to the 10th over B to the 6th is B to the 4th. There's a rule that says you subtract the exponents in this case, but then common sense tells you if you got B multiplied by itself 10 times in the numerator and 6 times in the denominator, you can group 6 of the B's in the numerator along with the 6 in the denominator, and it gives you 1, leaving you 4 B's multiplied by each other to B to the 4th. You should understand it at that level. Otherwise, you're going to be apt to get confused when you apply the laws of exponents. You have to understand why they work because they can be confusing. And it gets even a little more confusing when you throw in the laws of logarithms, which we're going to get to next week. So we can solve exponential equations among other things. Okay. So we get 12 equals 21 B to the 4th. So okay, that 12 is, that 2 to the 12 is written a little small, but you see it's going to be 12 over 21. Okay, which is, of course, 4/7. Well, we'll come up here. Write that again, B to the 4th equals 4/7. So how do we get B? We raise B to the 4th to the 1/4 power. Well, B to the 4th to the 1/4 is B. To the 4 times 1/4. That equals 4/7 to the 1/4. Now, ballpark, that's 0.6 to the 1/4. A little less than 0.6. I know that 0.9 to the 4th power is 0.63 roughly, so 65. Okay. So I'm going to say that's about I don't know if it's 0.89 or 0.88. It's good. the calculator if you have one, but I think it's gonna be somewhere around that, a little less than 0.9. Okay. Only a few misgivings about that. But yeah, I think that's probably fairly close. Okay, so anyhow, we get a value for B in the algebra is just really fairly straightforward algebra. You just have to be careful about your laws of exponents. You can also take the fourth root of both sides. I prefer to use exponents just because of the way the laws of exponents are expressed. It's a little closer to the rules for exponents. But if you understand radicals, you can do that too. Okay. Well, now that we have B, and of course, the 0.88 is B to the 4 to the 1/4, 4 times B to the 4 times 1/4. 4 times 1/4 is 1. So we have B to 1 equals this, so B equals this. Approximately. Then what do? We take this value and we plug it back into one of the equations. And let's take that and plug it into, well, the most expedient thing would be to plug it in here, since we get a result almost immediately, okay? If we plug it in the equation, we've got a little more work to do. But I'm going to take this. I'm going to go ahead and plug it into equation 1. And we're going to get 21 times 0.8866. That equals 8 times. I'm saying 0.88 to the 6 is probably close to 0.5. Giving me A approximately equal to 42. And yeah, I'll go with that. It's not totally accurate, but it's reasonably close. Okay. So now what do we have? There we have, that's our function that approximates our radioactivity. Okay. Okay, so now my question then is, want to estimate the time for the activity to fall by half. I would say we're not going to try to estimate it based on that. We're going to solve it based on that. Or we're going to estimate and then we're going to try it. Okay. So we fell from 21 to 12, right? Okay. If the activity goes to half, it's going to go down to half of 21, which is 10.5, right? So half of 21 is 10.5. So we want to look on the graph and see about where 10.5 activity level of 10.5 is going to occur. We want to estimate that point on the graph. So 10.5, well, 10's here, and 10.5 is just a little over 10. Well, that's a big old coincidence because what's the what's the t coordinate look like here? Here's 10, here's 12. What do you think that is? Pretty close to 10.5, isn't it? So we get 10.5, 10.5. Well, that's just coincidence. I didn't see it out that way. And it's actually a little closer to halfway. So estimate 10.7, 10.5. Which means y equals 10.5 and approximately t equals 10.7. Well, now, I don't think it's going to work out real well. I think it's going to be real accurate, but probably reasonably close. So if you've got a calculator, just see how far I'm off. Plug in 10.7 up here and see what you get. Okay, one thing I want you to do is, well, if you have your calculator, you look at it and see you can do a log. Okay, there's a log key. So you do log of 1/2 divided by the log of 0.88. So it would be worth kind of doing that right now. Next week, we'll see why you would do that. Okay. Now, coming back to things that you understand at this point. You wanted to know the growth factor and the growth rate. Okay, what's the growth factor? It's the basic exponential function. It's the 0.88. Okay. What's the growth rate? If your growth factor is 1, add a 1 here to the t, then y wouldn't be changing at all, right? Growth factor is 1. That means your growth rate then is 0. You're not growing, you're not shrinking. Okay. If I have 1 to the t, it's always 1. So this would always be 42. There'd be no growth, no decline. In this case, there's a decline because this number is less than 1. And when you take a power of a number less than 1, you get a smaller number every time you increase the power. Okay. You take a positive power, you get a number that's less. Okay. So the growth rate is intuitively we compare the 0.88 to 1. 1 is 0 growth. Okay. 0.88 is 0.12 less than 1. Okay. And it's going to be 0.88 minus 1, which is negative 0.12. 0.12 is 12%. This is a negative 12% growth rate. Does that make sense? Well, yeah. If you multiply something by 0.88, it gets 12% less. So to understand this idea of growth rate, you multiply a number by 0.88, that number is going to decrease by 12% because 0.8 is 12% less than 1. If you multiply the number by 1, it wouldn't change. If you multiply it by a number that's 12% less than 1, you're going to get a number that's 12% less. That's an intuition that a good understanding of percents would make obvious, okay? So try to understand percents well enough. That's really an obvious statement because it really helps with understanding exponential growth and decay. Now, this is an example of exponential decay. With a growth rate of negative 12%. Decay means it keeps decreasing exponentially. It means it follows a curve like this, which is just your basic exponential curve flipped around the y-axis. Okay. What's the growth? So the growth rate to emphasize it much more. Take all the extraneous words out of this. The growth rate is negative 0.12 or negative 12%. If it's a population that's declining because the environment suddenly changed. Okay. Your fish pond suddenly got a lot warmer and you're trying to raise trout. Okay. Population is going to tend to decline exponentially. You might not kill individual fish, but you're going to decrease the reproduction rate. Okay. Or maybe you cool it off and your growth rate becomes 12%. They reproduce because they like cold water better. Okay. So one way or the other, these growth rates have interpretations in many different situations. The one I used just quickly in a previous class, I've got this liquid bandage, and it's very handy because this thing chafes my hand. It's, it's actually a little boo-boo there. I don't want boo-boo on my hand. It hurts. Okay, so I take this stuff, I open the cap, and I smear some stuff on it, and I close the cap, and it's somewhat protected. Okay. Every time I open the cap, fresh air gets in. It interacts with the stuff that's in there and makes it a little bit thicker. And this one's getting to the point where it just about doesn't pour, but still works. But very soon it's going to get so thick that I can't even get it out of the bottle. Okay. So what's happening there? If I use this once a day, then once a day air is being exposed and it thickens whatever's in there a little bit. Okay. The less that's in there, the more it's going to thicken from that given amount of air, because that amount of air is acting on a smaller volume of the chemical. Does that make sense? So that air does a certain amount of thickening. If it does a certain amount of thickening in a swimming pool of this stuff, it doesn't matter much. If it does it in a thimbleful, it makes a big difference. Well, that's kind of an exponential increase in the thickness. Okay? Because the amount of thickening, or the amount by which the stuff gets thicker, is proportional to how much is in there, inversely proportional to how much is in there. Well, just another example of an exponential function. That one's not really exponential because the chemistry is much more complicated than that, but you kind of start off with the idea this thing kind of has an exponential behavior. It exponentially thickens. We had a very good question there. Couldn't you also say it's an exponential decrease in quality? Well, that depends on how you define quality, but there would be definitions of quality, which is just inverse to thickness. Okay. And if quality is inverse to thickness, then you have an exponential decrease in quality, assuming you have an exponential increase in thickness, however you measure that. And there are various ways to measure thickness. Okay. Viscosity. These are the first things that popped into my feeble brain. But again, it wouldn't be perfect. Among other things, the less stuff you have, actually, the more air goes in. Okay, so that's going to be a factor too. Maybe it turns out to be linear. I don't know. I'd have to test it. And at $1.50 a bottle, I actually could, but it would have to be done over a period of weeks or months. And I probably have other things I need to do first. Be interesting. I'd like to do it. Maybe we'll get my 9-year-old grandson to do that one. Okay, let's talk about the graph of y equals 2 to the x plus 3. We can graph that. We just graph y equals 2 to the x. There's y equals 2 to the x. You get y equals 2 to the x plus 3. We simply raise every point 3 units. So we raise this point up 3 units, raise this point up 3 units, raise this point up 3 units, and we do the same for this point down. And this point. If I was just given this graph and told there was an exponential function, how would I determine that it's a 2 to the x and it's being raised by 3? Well, I can look at what happens between here and here. Okay, between this point and this point, I move over 1 and I move up 1, right? There's a little more that I'd like to say, but I don't think we have time, so. So I could say, okay, F0 equals 4, F1 is 5, F2 is 7. Have to rely on open math. They don't have time to say everything I need to say. F changes by 1, then it changes by 2 on equal. Okay. So you divide this number by this number, and there's your base. That's what it comes from. So unfortunately, spent a little more time on this than we do on this. But that should give you a hint that you're going to be asked in some cases to figure out an exponential function. We're just given a function that's been raised or lowered, and you have to use the evidence to figure out how the function, what the function is. Okay, I think you'll be okay with that. I apologize for not having spent a little more time giving you the whole idea. So we'll see how you do, and we'll straighten it out next time if necessary.